Hi there. We are talking about section 3.1, increasing and decreasing functions and relative extrema. We have tackled discussing increasing and decreasing. We're going to try to look at defining critical points and relative extrema in this video. Let's get ourselves there. Okay, so this is sort of a funny word, extrema, but just to put in context the two words we're looking at here combined into one piece of terminology, relative just means in a small little area. So another word that gets used for this sometimes is local. And then extrema is the plural of extremum, which doesn't make your life any easier. But really what we're thinking about is either a max or a min value of some function. So the notion of a local extremum is interesting because usually we think, oh, well, what's the biggest of all time or something? But it turns out that what calculus is particularly good at giving us is the location of maxes and mins just in a little neighborhood. So sort of the mayor of a town instead of the king of the world. So this is kind of a dense definition, which is why I wanted a little preface first. So relative maximum, so just thinking about max first, is some value, an input, such that if you look in a little area around this place, so you pick some x values and you look at the function outputs, what you get are things slightly smaller than that point. So for instance, here's a point at the top, so this could be an input of m. If we pick x values in a little neighborhood around this, then what we get are numbers that are either about as high or slightly smaller than the value at m. So we think of this as a relative maximum because it fits this criteria. If we look a little bit to the left, a little bit to the right, this is the largest value. It doesn't matter, actually, if this function later on sort of circled upward and there's actually a point higher on the graph than over here. This is, in its little area, it's a maximum. So it doesn't actually care what goes on in the rest of the function. Relative minimum works the same way. I'm picking a different letter to work with just so we don't get confused, but big M and little m to think max and min for small. And basically it's the same definition but with the inequality reversed. So here it's greater than, here it's less than. So if all if in a little neighborhood around this point all these values are larger than it, so we've got something down here, then we call that a relative minimum. Again, the same stipulation. It could dip down really far later on, but in a little neighborhood right around this point, this guy is sort of the bottom of that valley. Okay, a related topic, and then we'll put these two things together. So critical point, we'll pick some input, so we're calling it C that works for F, and then basically there's two cases. If f prime at that point is 0, or if f prime is undefined, then we say that C is a critical point, or that f has a critical point at C. And I want to put a lot more focus on this first condition. This is still an important one. It can come up in certain instances, but I would say probably 95% of the time the cases that make sense for business are going to be this former case where the derivative is equal to 0 rather than kind of this confusing one about being undefined. The reason we choose this moment to talk about critical points is that relative extrema can only occur at these values. So if we want to look for a relative max or relative min of our function, where it makes sense to look first is a critical point. So just a quick example to get us in the neighborhood, no pun intended. So we've got some function, and we've got a nice cubic here, and the critical points would happen where the derivative of this thing, so let's think we got some power rules, so the 3 would come down, cancel out this 1/3, so we'd have negative x squared. The 2 would come down, cancel out this 1/2, so we'd have negative x, and then plus 2, and the constant all by itself would be out of the mix. So they occur when this derivative is equal to 0. So it turns out we can factor this a little bit. It would be just fine to do quadratic formula or something like that as well, but this gives us two solutions, x equals 0 and x equals negative 2. So what we can conclude from that is that f has critical points at x equals 1 and x equals negative 2. So we're going to make mention of this later on, but So one thing to think about is that just from this what we've talked about so far, I don't have any idea if this is if at x equals 1 there's a maximum, or if there's a minimum, or if neither, in fact, because we actually can have a critical point and have neither a maximum nor a minimum at that critical point. So the three basic graphs we can think of, if the derivative goes to 0 for a split second, we could have this particular picture, which would comprise a maximum for that input. We could also have the upward opening one, where we've got a point down at the bottom there. So this would also be a place where the derivative, the tangent line, if you will, would go horizontal for a split second. So this would be a critical point, and it would correspond to a minimum. And then yet a third case, we could have what's sometimes called a saddle point. So here's a point right in the middle where the derivative actually does go to 0, but this point does not correspond to a relative max or a relative min. There are values that are lower than it on the left and bigger than it on the right, so this isn't a max or a min. So all I'm saying is, just by finding that there's a critical point somewhere, I don't know which of these characteristics is actually the case. So what we're going to come up with later on is a criterion for how to determine whether a critical point is a max, a min, or neither. For right now, we're going to try this with a function, and we're going to use the graph to our advantage, which is always a good idea. I would always encourage having a graph available of some function, which is why graphing calculators are not discouraged at all here. Okay, so we have a number of things to accomplish, though. Find all critical numbers, classify them as relative max, relative min, or neither. Okay, so one thing that I'll end up reiterating hopefully a number of times because it's important and it's easy to mistake. The claim is that if you want to find a relative extremum, that is a relative max or relative min, then you have to look at critical points. That does not mean that every single critical point is going to be a max or a min. We already saw one case a minute ago, the kind of saddle point thing, where a critical point did not correspond to a maximum or a minimum. But that's where we start anyway. We find critical points by setting the derivative equal to 0 or finding where it's undefined and solving. So here's the case where we get most of our solutions. So we're going to take the derivative of our original function, set it equal to 0. So our derivative looks like, all right, well, we can do this. 4x would just be 4. And then this is some power rule. Maybe we want to rewrite this a little bit first. The fraction piece can be rewritten in a form more useful, more evocative of power rule. So 2x to the negative 2 power, so the negative 2 would come down. And the exponent would be decreased by 1. So you'd be at an exponent of negative 3. Okay, well, trying to get busy and doing more than one thing at once here, we've got the 4 coming over to the left side to get negative 4, and then just multiplying these two terms together. So 2 and negative 2 make negative 4. Divide both sides by negative 4. And then you could think of this a variety of different ways, but if you raise both sides to the negative 1/3 power, which is kind of adorable, but whatever it takes to make this x to the power of 1, basically. So we're picking an exponent so that when they get multiplied together, we get an exponent of 1 when we're done on the right side. But okay, that's fine, because 1 to whatever power is pretty much still 1, so we'll get x as 1. So that covers the case where most of our critical points come from, but we also need to look at the case where the derivative is undefined. Okay, so we'll go through this a little bit rapidly, again, mostly because our attention doesn't usually need to be dedicated to this particular task. But so here's our derivative, which we already computed. It's undefined when x is 0. Remember, that's because this is really 1 over x to the negative 3. So if we have 1 over x to the third, so if x were 0, this expression would be undefined. So that's actually a tempting spot. But this is an important detail. Yes, the derivative is undefined at x equals 0. But f, the original function, is also undefined at 0. You can't have a critical point at a place on the graph if there's no place on the graph to have a point. So in other words, you can't have a critical point if there isn't actually any point to begin with. You can't be a special kind of point without actually being a place on the graph. So because f is undefined at 0, it doesn't matter that f prime is undefined at 0 as well. There can't be a critical point where there's no point on f. Okay, so really we've only got one critical number. And I sort of think about this like a job interview. You've got one candidate for your job. There's at least a couple different positions that could be filled, relative maximum, relative minimum. But just because you interview somebody doesn't mean you have to hire them. It doesn't mean that just because x equals 1 is our only candidate doesn't mean he's going to be both a max or a min or either one of them. Maybe he's just not a great candidate and we don't hire him. But we're gonna put him through the trial anyway here. So here's the basic process, and we're gonna give this a name here pretty shortly. But so our task is essentially to look at x equals 1 and then evaluate the derivative to the left and right sides of this. What calculus has basically done for us is guaranteed that at x equals 1, the only time this function is allowed to change its mind, that is to go from increasing to decreasing, or vice versa, from decreasing to increasing, is at this point. So if I test to the left and the right of this value, any parts of this function that are defined, I guess I should say, I can't pick any numbers, but anything that's defined in f prime, then we should be able to figure out whether this graph is headed up or down over that entire interval. Because what calculus has done for us is say any inputs to the left of this are going to either always be decreasing or always be increasing. It can't switch directions in the middle. So we can pick any point. I picked a test point of 0.5. That's just because I couldn't pick 0, that would be undefined, and I wanted something to the left of 1. But anything would do. 0.75 would work, 0.1, 0.3, 0.999 would all be fine. So we would get a different output for the derivative, but it would be the same sign. It would be either positive or negative always. So since this number is negative, every point evaluated to the left here would have a negative derivative for this function. So what that implies for us, since the derivative is negative, it implies that f is decreasing. And we can denote that with just this little arrow thing. We also need to test something on the right side here. I try to use whole numbers whenever possible, so I think I'll just go with 2 for a test point. That's certainly a number to the right of 1, and it doesn't involve weird decimals and stuff. So if we compute that, we plug that into f prime. Again, we're using f prime as our determination of increasing and decreasing, because the derivative is all about slopes. So if we take 2 and dump it back into our derivative function, we get 3.5. And really the only thing important about this number is that it's positive. So that means that f is increasing. So there's our little diagram, and it's showing basically that for values less than 1, the function is decreasing. For values greater than 1, the function is increasing. So what that seems to be implying is that there's a relative minimum at x equals 1, because the graph is headed downward on one side, downward to the left over here, and then upward to the right. And then a graph should be able to back this up. So we could look down there at x equals 1 and feel pretty confident that, yeah, see, the graph is headed downward everywhere up to that point, and then from that point forward, the graph is headed upward again. So we should feel like that's a relative minimum. Okay, so that's it for this video. We'll be back with one more word problem and a formalization of what we should call this process of determining whether something's a relative max, relative min, or neither.